Stress is force all over area. But remember, in front of this stress, you have normal. So your normal stress is normal force divided by area. Whereas for shear stress, is shear force or tangential force, tangential force acting tangent to your area, tangential force divided by area. So always remember, when you hear the word stress, it's always force bahagi area. So force, normal stress, normal force over area, shear stress, shear force all over area, or tangential force all over area at all. And like I said, for your normal stress, we are going to use sigma. And for your shear stress, we're going to use tau. All right, so just to recap what I said, we are going to divide your stress into two, which is normal stress and shear stress. Normal stress and shear stress. And your normal stress is the magnitude of force per unit area acting in your normal direction. That's why we say it's normal force divided by area. That is the force acting in the normal direction. So for example, if this is your area of consideration, your normal force is this one because this is acting in the normal direction. Whereas this is going to be tangent. This is your tangential. So your shear force will act in this direction. And for normal stress, we're going to denote it. We are going to use the symbol sigma. Now, your normal force could either be a pull or if it's a pull, you are pulling away. That is tensile. If it is a push, then compression, push, tensile, pull. So if it's a pull force, then it's tensile. If it's a push, it's compression. Then again, your shear stress, like we said, is the magnitude of force per unit cross-sectional area acting tangent. That's why we said shear force is equal to tangential force divided by area. That is force acting tangent, not normal. This is normal, this is tangent. Acting tangent to the area. So here, your shear stress, we are using tau, and for your shear force, we are using V. That's just a symbol we'll be using for consistency. So for your normal force, we'll be using F. I think sometimes we use P over A. But this is just still saying normal force, depending on what we define. Any question with that? Any problem? If I'm too fast for you, please let me know. Ada soala, nada masala. Where is my chat? Hello. Ada orang sana.
Doctor.
Cakap.
Ada.
What is V?
V is shear force. Shear force or tangential force. And this is normal force. Okay, Afif. All right, so okay, Kasi. Okay, supposed to. Now we're going to be looking at average normal stress. So first we'll be looking at normal stress, then we'll come back and discuss shear stress in detail. So your average normal stress is force divided by area, where your F is a resultant of the internal forces over the cross-section area. And your sigma is your average value of your stress. So if you have your internal force normal to the plane of the area, then it's called normal force. So we would consider the average normal stress, but like I always say in FTK or FTK-MP now, what we are interested in is applicacy. How do you apply this to solve problem? We are no more interested in sigma is equal to F over A now. We want to see if I'm sitting on this chair in my office and my weight is 60 kg. How much stress am I going to put on this chair? Then how do I do the analysis? That's what we are interested in, applicacy. So then, very quickly, procedure for analysis. Procedure for analysis. Number one, remember, your stress is equal to force over area. So the first thing you need to do is you need to calculate your force. You need to obtain the internal forces acting on the body. What are the forces acting? You need to be able to calculate. And for you to do this, you need to cut the member to its longitudinal axis at the point where you want to determine the normal stress. Now you need to be careful. You need to only concentrate on where the stress is to be determined. Then you draw the free body diagram. You draw the free body diagram, and after drawing the free body, the internal forces. For example, I have this. Here I have 10 kN. This is A, this is B, and this is C. And here I have just 2 kN, and I have another 2 kN here. Then here I'm going to have 6 kN. Now I want to determine the stress at AB. This is A, this is B. I want to determine the stress in this region here, AB. All I need to do is cut this, determine the force acting on AB, then draw my free body diagram, use EOE to determine the force. So that's what we are saying. If I'm going to consider the stress acting on region BC, then I'm going to cut here. So you cut at the point where the stress is to be determined. We'll be looking at examples as we go along. Then after you get your F, so step one, obtain your F. And for you to obtain F, you cut, draw FBD, use EOE. Then step two, you need to calculate your area because now you know your force. You need to calculate your area. This is step one, this is step two. Step two, obtain the cross-section area. Determine the cross-section area at the section member. So you need to determine the cross-section area. Diane, you're asking to control what?
No, something is wrong with my laptop. Sorry, sir.
Okay. I want to decline, but before I decline, I need to seek your consent to know what you're up to. Okay, that's fine then. Okay. So then the next thing is for you to calculate or determine the cross-section area of interest. Now, after you determine the area, where are we? No, so area now, that laggy stress. So all you need to do after you get your force, you get your area, then you use this formula to determine your stress. So step number 3, obtain the average normal stress. So you compute the average normal stress using F. It says sigma is equal to F bahagi area. Ada soalan. Ada soalan, ada masalah. Saya tak boleh faham lah kenapa apa.
No, sir. Paham, sir. Paham.
Paham eh?
Paham, ya.
Semua
Tak ada masalah,
kawan-kawan
sir. Tak ada
okay
masalah.
Tak ada masalah. Terima kasih ya. Okay, so let's look at one example to actually understand better. Like I always do, my is we look at the procedure of analysis, then we try to solve one problem. It more clear. Let's look at this example here. You have a lamp holder. It's made of two rods. Rod 1, AB. Rod number 2, AC. Rod AB has a diameter of 8 mm. And rod AC has a diameter of 10 mm. If the lamp has a mass of 60 kg, determine the average normal stress, okay, acting on AB and AC. So here now you have two problems. One, you want to determine sigma AB, lagi sigma apa?
AC.
Terima kasih. Cari sigma AB lagi sigma AC. So now sigma AB equals apa? Sigma AB equals, what is sigma? What's the formula for sigma?
Force over area.
Force over area.
So ni F,
Force over A.
for ni AB, so ni FAB bahagi area AB. Because the diameter of AB is different from diameter of AC. So ni area AB, AC tasama. Tasama. Ni 8 mm, 8 mm, ni 10 mm. So then, sepas tu, sigma AC equals FAC
AC
bahagi
over AAC.
AAC. Thank you. So now, from this, FAB ada. Tahu tak tahu? FAB tahu tak tahu?
Tak tahu.
Tak tahu.
Tak tahu.
FAC tak tahu juga. So first, cari FAB dan FAC. Boleh? So what you have is this. So ni FAB, FAC. Okay. Then ni 30 ya. Sini okay lagi this one. 45. So ni weight equals, what is weight? Formula for weight.
Times
MG, thank you.
MG.
MG. So M berapa? Soalan M berapa?
60.
60. 60.
M 60 darab G 9.81. So ni berapa? Faham tak faham kawan-kawan?
Faham tak, faham tak?
5
Faham doktor, faham.
588.6 Newton. So now, ni ada, yang ni ada, ni tak tahu, ni tak tahu. So EOE, summation F of X is equal to 0. X direction berapa forces? Dalam S direction. Ni FB dia. Sini 2. So FAB sin atau cos. So what are the forces? FAB. I'm waiting for you.
45. Cos 45.
Apa? Cos
Cos
45.
45.
Okay. Tambah tolak.
Minus. Tolak.
Kenapa tolak? Kenapa tolak?
Sebab FAB tu saya dah buat positif. Dia equivalent.
So ni kiri,
Opposite direction, sir.
yani
Kiri
kanan.
equivalent.
Direction tak sama. So ni kiri positif, kanan negatif. Faham tak faham?
Faham.
Faham.
So ni tolak FAC apa?
T.
FAC
Cos
Cos
30.
30.
cos 30 cos 30 degrees. Okay, so then equals 0. Then summation f of y is equal to 0. Berapa forces dalam y direction?
3.
3.
3. So ni FAB sin 45. So sekejap So ni atas, ni bawah. So tambah FAC sin 30. Is that correct? Tolak
30.
Tolak 588.6 Newton equals 0. So cari FAB dan FAC. Kawan-kawan cari FAB dan FAC. So you find your FAB and FAC, then you type for me, I see your answer. If you have problem, please, you can either chat me privately or you ask your question, no problem. I'm watching your chat here. Just in case you are shy. But don't be shy. We are here to learn together. We are working together. So, Suma orang cari FAB dan FAC.
Okay, sir. Okay.
Okay. Thank you, Logan. 430.89. Okay, Logan, terima kasih. I'm waiting for others, please. We all have to do it. Okay. Okay, thank you. No Africa. Mohammed Azaem, thank you. Nuru Fahima, thank you. Terima kasih. No Iswine, thank you. Okay, kasih juga, kasih. Lagi. Mana kawan-kawan sana, Thank you, Muhammad Tajuddin. Let's be quick so we can continue. I'm waiting for others. Nasiruddin, Adam, terima kasih juga. I just want you to be part of this class. Please participate. That's what makes you part of us. All right. So thank you, guys. So we just continue from where I stopped. Okay. So guys, please make sure you try these things and you know how to do it. So like I said, the first thing is you draw your free body diagram. Because step number 1, you want to determine the internal loading. So FBD, then EOE. And from your FBD, you calculate your weight. Then from there, you can calculate FAB and FAC. And if you do that correctly, you're going to get something like this. Okay, who got 524? Mohammed Amal, is it 524 or 523? It's all right, whatever you get. But you should get something like this. FAC equals 430.89, FAB 527.798. Right, now let me stop here and ask you a question. What are you supposed to find? What did they ask you to find? Chari Apa? Sualan Chari Apa? Stress. Thank you. Ni untuk apa? Nyanyi apa?
Nilai bagi F. The value
Ni
of F.
F.
Pause.
So ni F. So if you stop here, then you have not finished. So now you need to calculate your stress. Stress AC equals FAC darab bahagi AAC. AAC area is equal to pi d squared all over 4 or pi r squared. AC diameter untuk apa? AC
Rod for AC. Diameter rod.
AC diameter mm. AB diameter 8 mm. So substitute D dalam formula ni, then cari AC. Then lepas tu cari AC sigma AB. Faham tak faham?
Faham, sir. Faham.
Hello? Okay, so from here now, substitute your diameter here, diameter AC. Then for AB, you substitute diameter AB. Then you now calculate your sigma AC down sigma AB. So now I want to see your sigma AC and sigma AB. So what you have is sigma AB is equal to F AB all over AAB, which is your FAB is what? FAB is 430.89 divided by pi. Your D is 8. But you convert this into meter. I will prefer you convert it to meter. That's 0.008 squared all over 4. Then the saving sigma AC is FAC all over AAC, which is 527.798 divided by pi into 0.01123 squared by this squared all over 4. So you can get your answer here and your answer here. So I'll wait for you again to do that. I just want to make you part of the class, so I don't just talk everything and say everything and do everything. So let's do it together. We can Ole. So sorry. You are writing that wrong. FAB 52. Oh, sorry. So this is AC. Thank you. AC, this is AB. So this is B, C, C, and this is 10, and this is 08. Thank you. No, Sarah, thank you. Very much. I say that is to show that you are following the class. Well done. So then I need everyone to respond. Then we continue. We have a lot to do today, so let's be quick, guys. Right, so let's see where we are. Right, thank you guys. I think these guys are responding quick, so we are good to go. 10.5 done, 5.4. Oh, 10.5, 5.49. Terima kasih. From Mohammed Azim. Logan. Terima kasih. Okay, so that is it. Let's continue from your lecture notes, guys. We are good to go. All right, so all you need to know now is to determine your stress. And for you to determine your average normal stress is sigma AB equals FAB IE area AB. So you substitute. Here I'm using pi r squared. Pi r squared delay by d squared over 4 superlay. Sama. Okay. So any question with that before we continue? Ada soalan, ada masalah. Saya tak tahu lah. Thank you. So any problem? Ada soalan?
No, sir.
Semua baik, eh?
No, baik.
Okay. Now, if you look at what we considered before, now we're looking at average normal stress. Now let's give you another scenario. I want to give you a case study here to look at. Where is my reason? Let me remove this one now. I want to draw something here. Now let's assume you have this rod here. This is A, B, C, and D. There is a force here, let's say it's 10 kN, that's okay. I have 2 kN here. I have 2 kN here. I have 1 kN. I have 1 kN. So that is then here I'm going to have about 80 kN. Now if you look at this, how many forces do I have here? Satu, dua, tiga, empat, lima, enam. Now if the diameter of this is the diameter D is equal to 6 mm. What this implies is your stress here, excuse me, your stress sigma AB, sigma BC, sigma CD. Are they going to be the same? Is sigma AB going to be equal to sigma ACBC? And is it going to be equal to sigma CD? Is this correct? Is it going to be equal? It's not equal, and this is not equal, so this is correct. So if sigma AB is not equal to sigma BC and it's not equal to sigma CD, what this means is either here or here, you are going to have your maximum stress. Say for example, AB is 2, okay, 2 Newton per meter squared. Here you have 5 Newton per meter squared, and here you have 3 Newton per meter squared. Just an example. So in this case, when you have the maximum, BC. So one of the problem you can see is in some cases you may have to calculate where you have the maximum stress in an object. So we'll be looking at how to determine your maximum normal stress. Maximum normal stress. Now, in the previous example we looked at, both your axial force and subsection area were constant. But for such problems, where your normal stress and your area is constant, then you just calculate your average normal stress, which is force over area. However, there are some few occasions, there are some times where the body is subjected to several forces like this one. Or you have this. A, B, and C. So here you have 10 kN, and here you have 10 kN. Your area here, this is 1 and this is 2. Your stress at 1 is not equal to stress at 2. Why? Why is your stress not same? Because ni 10 kN, ni 10 kN. So kenapa stress tak sama? Different area sini beza ni kanche. So area tak sama and your stress is force over area. So area tak sama, force tak sama lah. So in this case, your stress is going to be bigger in one, either in 2 or in 1. So in those cases, you need to determine the location. Okay, then it is necessary to determine the location where the force is more. where your stress is maximum. So we want to see how to determine the maximum stress. We'll look at one example. This is an example here. Right. So here you have to determine the maximum stress in a rod having a diameter of 12 mm when subjected to loading as shown below. Now, to do this, like I said at the beginning, you need to determine force at AB, that is between here and here, FAB. Between here and here, FBC. Between here and here, FCD. Now, and for you to calculate your FAB, FBC, and FCD, you put on. For FAB, put on the alarm AB. For FBC, put on the alarm BC. For FCD, put on the alarm CD. Faham. Okay, so let me draw here, and then we look at it together. You have this one. You have this one here. And you have this one here. Okay. This is A, B, C, and D. Here, 20 kN. Here is 6 kN. 6 kN. This is 4 kN. 4 kN. And this is 16 kN. Okay. So now listen to this. When you cut at AB, for example, I'm cutting at AB, put on Cine, ada satu ini kiri, ada dua kanan. Kiri boleh, kanan boleh. If you are starting from the left, you start from here to here. If you are starting from the right, you start from here to here. You cannot start in the middle. So you must start from the left. Oops. You must start from here to here, or from here to here. Because I know that gives my student problem. I will explain this. Okay. I'm going to do AB, then you do BC and CD. Okay, so if I take this one, let's see what we have. I want to draw my free body diagram. KN. Ini PVB FAB. Summation F of X equal to 0. FAB berapa? 20 KN. Simple. That is kiri. Kiri boleh, kanan boleh. Okay. Everybody okay with this? Faham. Logan. Okay. Now I'm going to do from the right. Let's see from the right now. Sorry, I'm doing this so I can have space for me to explain for you. So if you are writing, you need to write fast. Okay. Now I'm going to do the same thing from the right. If I'm doing from the right, I will go from here up until this point. I cannot stop only here. From the right, from here to here. Ni 16 kN. Sini ada 4 kN. 4 KN lagi. Sini ada 6 KN. 6 KN. Now this is 4. This and this and this are going, so this one will come this way. And this is my FAB. Faham ta faham. Now I cannot stop only here. Okay, let me just project this down. I cannot do like this. Ni tabule. Tabule. If you are coming from the right, you come from this end to this. If you are coming from the left, you come from here to here. So you cannot stop in the middle. Faham ta faham. Okay, so ni tabule. So yani EOE, lagi EOE now. Summation f of x equals 0. Now we use this positive. So ni FAB tola tamba. Kiri positive kanan tola. Ni tola.
Tolak.
Lagi tola. Ni
Tambah.
tambah. Lagi tambah. Ngani
Tolak.
16.
tola. So FAB berapa?
FAB
20.
20.
Apa?
20.
FAB equals 20 KN. So kiri 20 KN, kanan 20 KN, sama-sama. So FAB 20 KN. So now cari FBC. Potong dalam BC, cari FBC. FBC. So cari FBC, quick. Then we continue. After FBC, we go to FCD. FBC, cari FBC. Okay, let me rub this off so I can just show you what to do here. So potong sini. So cari FBC. FBC. Come on, guys, let's go. Jawapan mana?
Wait.
Okay, sekejap ya.
Sekejap.
8, terima kasih Syafiq. Iqmal, 8, terima kasih. Adam, terima kasih. Syuaida, terima kasih juga. Bastria, terima kasih. FCD, oh, somebody already FCD. Ayolah, I'm very fast, eh? Tajuddin, terima kasih, eh? Okay. So, ni 20. So, ni So, ni 12 tola 28. Okay? Ada soalan? Ada masalah? Okay, then FCD. FCD. No isuan, terima kasih. Aman, terima kasih juga. Terima kasih, Iqmal. Logan. Oke, terima kasih Logan. Okay, so now FAB, 20 KN, FBC, 8 KN, FCD, 6 KN. So now you cari your diameter berapa diameter? Diameter berapa? Diameter 12. Diameter 12, 12. So you cari your stress. Stress AB, stress BC, stress CD. But since your diameter is same, diameter sama, then from here you can determine your maximum. So maximum location mana? Maximum tempat mana? A, B, B, C, C, D. Maximum.
AB.
AB.
A, B lah. A, B 20 ni 8 ni 16. So AB is your maximum. So you just calculate your maximum, finish. So you calculate your stress at maximum. Faham tak faham? Okay. All right, so this is what we've done so far. The maximum. Then from there, we can calculate our maximum stress, which is FAB bagi area. Ada soalan? Ada soalan, ada masalah?
Tak ada.
Semua baik.
Baik.
Faham? Okay.
Yeah.
Please, if you have any question, let us know so we can answer your questions. All right, so with this one, I think I will stop your last week lecture. I'll be going into what we have today. Okay, this is just for last week. I just have to finish this. So if there's no question, I will be going into shear stress now. We've done more of normal stress, so we'll begin shear stress. So let me take this off, discard, don't worry. Let's go to shear stress. Okay. All right, so today we'll be looking at shear stress. Then if we have time, we conclude with strain. Okay. Do you have class after this? Hello?
For 1-1,
Guys? No class. Okay, if you don't have class, I will just extend your class and make sure I finish everything today. If you don't mind. For me, I'm happy to do. If you're happy, I'm happy. Apa?
Some of us have class. Coco.
You have class. Okay, so if you have class, then I need to stop by 2 o'clock. Okay, so let's just start something. So I'll be looking at shear stress now and strain. So I'll be introducing the concept of shear stress, and I'll be looking at normal and shear strain. Now, like I said earlier, average, excuse me, average shear stress is given as V all over A. V all over A. Where stress, your V is your shear force, and your A is your cross-section area. All this we've defined earlier. This is your shear force, this is your area, this is your shear stress. Basically, in many structures or objects, your shear force or your shear stress will act at the joints where they are joined together. For example, you have an object that is coupled together. This scissors is coupled together here. So if I have a force that I'm applying here, my shear force is going to act here. And this is going to act tangent to the force I'm applying. If I'm applying my force here, my shear force will act like this. So your shear force will always act at the bolt or the joint. And as a result, you can have what we call the single shear, double shear, or multiple shear. How do I mean? I'm looking for something to explain this better. Okay. You can see this here. Okay. If you see this, this is how you apply your force. Now, there's a joint here, there's a joint here. If I'm applying my force here, because I have two joints, one here and one here, part of the force I'm applying here will go here, the other will go here. So here now I'm going to have double shear, one shear here and one shear here. And here I'm applying only one force. So for me to get my shear force at this point and shear force at this point, I'm going to divide my force here by 2, half here, half here. So for double shear, my F, my V is equal to F all over 2. Because I'm applying my F here, this is my normal force. As a result of this normal force, the joint here is going to take part of it, and the joint here is going to take part of it. Whereas for these scissors, okay, I'm applying my force here. This is where I'm applying my force. There's going to be a shear force here, but we have only one joint here. So my F is going to be equal to V. My F here is equal to V because only one shear force here. And this whole force will go here as shear force. So for single shear, my F is equal to V, or V is equal to F. So the cross-section area of both, like I said, is going to happen at the joint. Both bonding surfaces between two members are subjected to single shear. So if you look at this now, you have one both here. So your F here is equal to V, or your V. So here you have V. So there's a shear force here, V. So here your V is equal to F. But when you come to this, here, how many boats do you have here? You have one boat, right? Hello? Can you hear me?
Yes, sir.
Okay. Here you have one boat, but here you have one at the top and one at the bottom. If you take this off, you can have something like this. That is one. And you can have something like this. At the bottom, this is another one. So this is 1, this is 2. Because this is joining 2 together. If you look at the first one, this is joining only 1. Only 1. But in this case, you have 2. So half will go here, half will go here. So your F here will be, this is V1, and this one is V2. So your F here will be, half will go here, F over 2 will go to V1, F over 2 will go to V2. So your V will be F divided by 2. Then if you have multiple, you have so many, like this. If you have like this, then if you look at this now, here I'm having 2F, half is here and half is here. So here at the top, how many boats do you have? Berapa boats? Ada 1, 2, 3, 4. So ni V equals F all over 4. Bawah lagi ada 4. F over 4. But if you are using this, then you have 4 atas, 4 bawah. So ni V equals 2F bahagi 8. 2F ni atas bawah. 4 atas, 4 bawah. If you use only F, which is only the top, then ada 4 sahaja. Bawah ada 4 sahaja. Okay. So here, what is your V here? Here, what is your V? F divided by, hello? Okay, F divided by 6 or 2F divided by 12. Thank you. So you can have single or multiple depending on the problem. So it is F over 4, and here is F over 6 or 2F all over 12. Thank you. Now, just a quick one, procedure for analysis for shear stress. Again, this is similar to what you did for normal stress. You cut at the point of interest, draw your free body diagram, use equation of equilibrium to determine your shear force. Then after that, you calculate your area, then you use your tau is equal to V all over A. So the procedure for analysis is same. The only difference is if you calculate your force, F, then you need to decide if it is single shear, double shear, or multiple for you to calculate your V. That is the only difference. I will look at one example, but this is not limited to this example. There are other examples. I think in your tutorial class, I'll be showing you another set of examples. But let's look at this example here. Now, a lap joint is fastened together using 6 bolts as shown in the figure. Each of the plate has a thickness of 10 mm. If the diameter of the bolt is 20 mm, determine the average shear stress on the bolts. So here, the first thing you need to calculate is you need to calculate your V. So what's going to be your V? V equals carry V. Carry V. V berapa? Terima kasih Nuru Karan. Ayo, very fast, eh? So V 60 bagi 1, 2, 3, 4, 5, 6. Or 1, 2 kosong bagi 6 darab 2, 12. Okay, so ni 10 kN. So V 10 kN. Then area. Cari area. Area berapa? What is the diameter of the boat? Diameter. Pi d squared all over 4. Pi darab konsol point konsol 2, 1, 2, 3 squared bagi 4. So cari area. Lagi cari shear stress. V all over A. So cari your area, then pass to shear stress. Let's do that. Calculate the area and your shear stress. So what is your shear stress? No, Iswan, Terimakase, 31.83. Fatin, Terimakase juga. Adam, Terimakase. Yes. Logan, Terimakase. Afik, Terimakase juga. Okay, thank you. So we just continue. So like I said, the first thing is you draw the free body diagram. From the free body diagram here, you can see that we have 6 shear forces. So for you to get the shear force on each boat, you need to divide by 60 if you are using the upper one, or by 12 if you are using the left one. Okay, so here you have this. Then the next thing is you need to determine your area. And your area is 5 squared all over 4. Then from there you use your formula to calculate your shear stress. Ada soalan. Ada soalan. Quick. Soalan masalah. Banyak
No, sir,
masalah. Banyak masalah. All right. Now I want to move to, if there's no question, then I think I just continue. I'll be looking at another thing which I call a liable stress. Now to explain this, I need to illustrate. Unfortunately, you guys are not on campus. It will have been easier to explain using the example of campus. But I guess you are in your second year, right? So you were here your year 1 first semester. You were on campus year 1 first semester. Is that correct?
Correct.
Okay. Now, how many of, I believe every one of you know the green building. The green building in FTKMP.
Yes.
Campus technology. Okay. In green building, berapa tingkatan? Okay, 7. Thank you. All right. So now you come in the morning. You have class by 8 o'clock in the morning, and you come there. How many people goes on the lift? 8 a.m. in the morning. 8 a.m. in the morning. How many people goes on that lift in the green building? Berapa orang? Average lah.
5 to 6.
You have class 8 a.m. and you are going on the lift 5 to 6? No, I don't believe you. If you come 8:30, okay, 8 a.m. and 8:30 a.m., how many people goes on the lift on an average? For 8 a.m., about 10. For 8:30, maybe 2 or 3 or 4 or 5. Because this one is peak time. Everybody is going for lecture. Here, everybody is already in lecture, so you have nobody going on the lift. Now, how many of you have checked how many people can enter the lift? In that lift, they will write Lapan Orang Sahaja. But during the peak time, boleh masuk. Depan sikit lagi. Boleh. Ini boleh masuk. Depan sikit lagi. 8 people, already 10. At times, 12. And the lift is still okay. Kenapa? 8 orang, now 12 orang. Ada masalah lah. But lift still okay. Why? Because of allowable stress. What happened is this. When you design, as a designer or engineer, when you design a product, say for example, the lift is going to fail at 1,000 1000 kilonewton. That is a failure. It's going to fail. You tell the user that this lead cannot take more than, you give them a liable load. You say the lead will only take 800 kilonewton or 600. What this means is you are only telling them you can take this, but if they go beyond this, the lift will still be okay. Why is this important? Generally speaking, people does not follow this during some time, especially during peak time. For example, I think I used to know my student last time. At the back of the car, they will put 4. At the back of your car, how many people are supposed to be there? At the back of your car, how many people are supposed to be there?
3.
Normally it's 2. It's designed for 2. It's designed for 2, but you're allowed to put 3 if there's no armrest in the middle. But over time, you see some students, 4 people at the back, 5 people at the back. Boleh. Campus technology, boleh. Masuk. Why? Why is the car still okay to carry you? Because the 2 or 3 you put there as allowable, that's just allowable. The load it can carry is more than that. So I'll be looking at allowable stress very quickly. As a designer or engineer, your primary design consideration when you are designing any structure is for the structure not to fail when it's in use. When you design any structure, your primary intention is when this is in use, it must not fail. And in order to achieve this, the stress level in the member must be set to a level where the member is safe. So if the maximum it can take is 100, that is, you need to look for a safe level, say 75. So you need to give people this one, but you know that it can take more than this. And the common approach to do this is what we call the factor of safety. Factor of safety. Your factor of safety is your F fail, which is the maximum, divided by your F allowed, Fs. Your F fail divided by your F allowed. So your factor of safety must always be greater than 1. If your factor of safety is less than 1, you are a bad engineer or bad technologist. So your factor of safety must be always be greater than 1. And depending on your applications and the material you are using, your factor of safety will differ. For example, if you are designing an aeroplane that flies in the air, because you'll be flying at 4,000 feet above the sea level, your factor of safety should be very high, about 20 or even 40. That's the factor of safety you use for an aeroplane. But if you are designing a car that just drive on the road, your factor of safety can be as low as compared to when you are designing something that is flying in the sky. So your factor of safety will depend on the type of application you're using. But like I said, your factor of safety must always be 1. For this case, what is your factor of safety here? What is the factor of safety here? This is failed. Allow. What is your factor of safety? 100 divided by 75. What do you get? Hello? 1.33. So like I said, your factor of safety must always be greater than 1. Fs can be expressed in terms of stress. So you can change your F fail to stress, and you change your F allowed to stress. So Fs can be F stress failed all over stress allowed. Now, to avoid potential failure of your member, your factor of safety must be chosen to be greater than 1. However, the actual value will depend on the type of material you are using and the application of the member. Like I said, for aircraft application, your factor of safety is always very high, very large. because you cannot compromise safety. If anything happens in the sky, that is it. Everything is gone. So your factor of safety, the value, will depends on the type of material you're using and the potential applications. But always remember that your factor of safety is your stress allowed divided by, your stress field divided by stress allowed, or your F field divided by F allowed. Okay, ada soalan. So always remember this. Remember this. It's important. Any question, any problem? Please, if you have, let's quickly say that, then we continue.
No, sir, no.
Others, check up. All right, thank you.
Faham, sir, faham.
Okay then. Okay, so then let's continue. Now I'll be going to design of a simple connection. Now, for example, as an engineer, you want to design a chair. The important things that is important to you. I'm sitting on a chair in my office. What is the thing that is carrying me on to sit on this chair? So if you want to design a simple connection, for example, if you are designing this chair, of importance to you is mainly the legs. The legs, the diameter of the legs. Okay. Don't break. The diameter of the legs. So then how do you design that? Let me do this. Remember, we said your stress is equal to force all over area. If you know the force, say for example, you know the F allowed is 80 kN or 80 Newton. That's okay. Oh no, you know the force. You just know the force. Then you know the stress allowed. Stress allowed to be say 250 MPa. From here, you can determine what's going to be the area of the leg of the chair. Because your area, your diameter, this is pi d squared all over 4. If you know this, then you can determine the diameter of the legs. And from here, you can determine the radius of the legs. So to design a simple connection, all you need to do is just know the force that is going to carry, know the stress allowed, then from there, you can determine the diameter. Let's look at this. Okay. So to design a simple connection, one of the key parameters is the cross-section area over which the critical stress is acting. Like I said, the stress is force all over area. So the area is very important. And to obtain the area of the members subjected to normal force, then you have this. Stress is equal to force over area. So from here, your area will be force all over stress. Here we'll be using your stress allowed for design purposes. And like I told you before, we can use this or we use P. And if it is shear, then you use V all over tau allowed. So there are steps for analysis. You consider the section where the critical stress is acting. Again, you cut, you draw your free body diagram, then EOE. So it's same procedure for you to determine the load. Then you calculate, you compute the required area, provided you know the allowable stress. If you know the allowable stress, then you can compute the area. And after you compute the area, you can determine what is going to be your diameter. Say, for example, your area is equal to pi d squared over 4. If you know the area, then you can calculate d. So then you can know the diameter of the leg, you can know everything you want to know, depending on what you have to compute. Right, so let me take 1 or 2 minutes to stop and allow you to ask questions before I move forward. Ada soalan. Ada soalan, ada masalah. Any question, guys? Come on, let's talk.
Okay, sir. Okay, no.
Okay. All right, so if there's no question, then I'll proceed to the next topic, which is strain. But before I look at strain, I need to look at deformation. What is deformation? Now let me allow you to talk. That I've been talking for some time. What is deformation? What is deformation? What is deformation? What is deformation? Let's talk, guys. Change in shape and size. Okay. Fail to go back to original size. Okay. Yeah, where are the others? I'm just reading. Or fail to go back to original shape. Okay. Change in shape and size when a force is applied. Okay. Is it only the ladies that are in this class? Only the ladies are talking. Where are the guys? Okay, Shafiq is bailing up the guys. Okay.
Yeah,
All right.
yeah.
The guys are sleeping, eh? Sumo Tido. Sumo Lelaki Tido.
Manado, sir.
Okay, let's quickly look at this. Can you see this? You can see this, right? Last week, I took something like this and I apply a force and I got something like this. Now, between these two, what do you think is the difference between these two? What is the difference between these two?
Shape.
Okay, somebody say change occur in shape. Okay, thank you. Now the shape has changed because here this is straight, this is bent. Now, what about the size? Let me put them side by side, okay? This one and this one. What about the size? Are they the same size? This one and oh, wait. This one and this one, are they the same size? I'm trying to see how to do it. Okay. Are they the same size? Looking at these two, do you think they are the same size?
Yes.
Yes.
Come on, I'm looking for how to do it better so you can see it better. Some people said yes. I don't want to agree with yes, so I need to make sure I put them side by side. Can you see my desk? This one? No. Okay. Can you see this? Let me put it back like this. Then I do like this. Are they the same size?
No.
Okay. So why? Because one, when I apply the load on this, there's a deformation on this. And as a result of the deformation, one, the shape will change, and two, the size will change. So if I ask you what is deformation, and you said it's change in size, or no, change in shape only, that is wrong. So deformation is change in shape than change in size. Change in shape only, wrong, because your shape will change and your size will change. That's why I've tried to show you from here that the size will change. That's why I put it on this. If you look at this now, you will discover that the size is not same. The two of them are sitting on the mobile phone here, but the size is different because the shape has changed and the size has changed. So basically, when you talk about deformation, it's change that occur in shape than size. And generally speaking, deformation could be visible, highly visible. This is highly visible. Here you can see that there is a dent on this. There is deformation. This is highly visible. And in some cases, it could be practically invisible, that you may not see the deformation except you look under the microscope. So your deformation could be highly visible or practically invisible. Now, one thing is important here. When a deformation occurs in a member, it occurs both in the axial direction and in the longitudinal direction. If your axial direction is increasing, your longitudinal direction will decrease. If your axial direction is decreasing, your longitudinal direction will increase. So it occurs in both directions, but in opposite magnitude. So if this is increasing, this will decrease. If this is decreasing, this will increase. So note that generally speaking, when deformation occurs, it occurs in both the axial direction, this is axial direction, and lateral direction. This is axial and this is lateral. Right. So with that, I'll be looking at strain. Because deformation is going to give me what I call strain. Now, I'm going to look at something here. Okay. I apply a force on this and it's producing this. Okay. So this is A, B, C, and D. And this is your A prime. This is B prime. Okay. Now, when you look at this, there are two things that have happened. We agree first that the size of A, DA, has changed to D. Is that correct? Is that correct?
Correct.
That's number one.
Yes.
Then number two, the shape here has changed
Prime.
to from rectangle to so from here now we want to look at strain. Your strain is related to your strain, like I said, I'll be dividing it into two, which is normal strain and shear strain. This is related to one, change in size. Change in size. This is related to two, change in shape. How do I know that the size has changed? From here, how do you know that the size has changed? What is the length? If this length is 10, what will be this length here? So if this length is 10, what will be this length here? Hello? If this length from here to here, DA is 10, what will be DA prime?
Maybe 8.
DA prime cannot be 12. From here to here is about 2 meters. So dA prime cannot be 12. It's shorter than 10. Yeah, it's not 8. From here to here is 8. So from here to here is not 8. But you can find out from here to here using the what's it called? X squared. X is equal to square root of this squared. Though this is hypotenuse, this is adjacent, this so it's 10 squared plus 2 squared or thereabout. So what I'm trying to say is your size has changed here. That means your change in size is as a result of length, which means your normal strain is change in length, because that's what results in your change in size. Is that correct? Yeah, use Pythagoras. Thank you, Logan. So this is change in length. What about shape? This shape is changed from rectangle to parallelogram or thereabout. Now, what is your angle here? And what is your angle here? Hello, your angle here and your angle here, is it same?
No.
Okay, so your change in shape, which is shear strain, is corresponding to change in angle. So I'll be discussing those two now based on change in length and change in angle. Change in length, normal strain. Change in angle, shear strain. That's what I want to explain here before I go forward. Don't worry, we'll be looking at it now. Okay. So like we said, we'll divide your strain into two. We have the normal strain and the shear strain. Your normal strain is your change in length. So the definition of your normal strain, the ratio of change in length to original length. So for example, I have this. I put this here. This is the initial. Because I'm pulling here, it goes up here. Okay. Now, from here to here is my original length. From here to here is my final length, LF. From here to here is my change in length, delta L. So my normal strain is denoted by epsilon. So my normal strain epsilon is change in length all over original length. Change in length divided by original length. And this is same thing as this minus this is equal to this. So you have your L final to la L original bahagi L original. So if you know your final length and your original length, you can calculate your change in length. And if you calculate your change in length, then you can calculate your normal strain. Now, let's give this a value. Let's say this is 10 mm, okay? My LF is 12 mm. What will be my delta L? And this is 12. What will be my delta L?
2.
Okay, so my delta L is 2 mm. Now let's calculate our strain. So from here, my normal strain will be 2 mm divided by bahagi
10.
10.
mm. So what's going to be my unit? What's going to be my unit?
No unit.
Mm cancel mm. So here, no unit. So for your normal strain, tada unit. And your change in length, if it is a pull, is elongation. If it's a push, is contraction. So if you pull, it increase. If you push, then it contracts, it becomes smaller. So for normal strain, change in length divided by original length. Simple. It's denoted by epsilon and there is no unit. Faham ta faham? Ada soalan?
Paham, sir.
Paham, sir.
Okay, so, okay, that's just description of this. Okay, let's look at this example here. Then after this, we continue. You have a rigid body, has a pin support here at point A with a wire. This is a wire. The wire has a pin support at point B. So it cannot live here, but it can move. Then you apply this force. Then this force push this down here. Okay. So C is moving downward. So from here to here is 20 mm. Now they want you to determine the normal strain in the wire in BC. So what's going to be your normal strain in BC? Strain in BC is equal to original length, change in length of BC divided by original length of BC. So your original length of BC, berapa? T. BC original length, berapa?
6 meters.
6.
So LBC is 6 meter. So your epsilon BC equals 6 meter here. What about the change in length in BC? What is the change in length in BC?
6.02.
20
No, that is
mm.
the total length. This is the
20
final
mm.
length. This is the final length.
0.02
Your
mm.
6.02 is your LF. Your change in length is just 20 because it's going down 20. That is the change in length. So that's 20 divided
0.02.
by 0.02. So then you can calculate your epsilon. So easy, eh? So easy, eh? If you want to use 6.02, then you have your epsilon to be 6.02 minus 6 divided by 6. Because your 6.02 is your final length. Faham ta faham?
Paham, paham, paham.
Paham.
So what is your epsilon? What is your normal strain? What is your normal strain?
3.3 power of -3.
Okay, I believe you. I don't know your answer, but I just believe you because I know you're a good student. Okay, so that's what you get. Thank you. Okay, no unit. This cancel this, no unit. Okay, thank you, thank you, thank you. So any problem, any question? You don't understand, please ask question. That's why I'm taking time. We do Satu Satula. Ada soalan, ada masalah.
Tak ada, sir.
Oh, you.
So far,
This
so
student,
good.
very good student. This student, very good student, eh? Okay, so let's continue. Look at this example here. Since you said no problem, then look at this example. You have from the figure below, as a result of loading, calculate the average normal strain on AD. So this is your original length of AD, and now AD is going to be here. So this is D prime. So they want you to calculate the normal strain. So first, your strain is equal to change in length all over original length. Original length. Or LF minus L original divided by L original. In this case, it is better to calculate your final length here. So what's going to be your final length here? What is your L original? Let's start with LO. L original. What is your original length of AD? So it's 300 mm. So now calculate your L final. L final. From here to here is 4. From here to here is 6. Okay, somebody said 300 minus 4. Now, from here to here is 300 minus 4, which is different from here to here. So what you have is this. You have this. If I bring out only this one here. So this is 300 minus 4. But this is what you want to calculate. So this is your 6. So you need to use Pythagoras theorem to determine this. So your LF is equal to square root of 300 minus 4 squared plus 6 squared. Do you understand? Hello? Okay, so this is what you're doing. So here is, from here to here is 300 minus 4. So you need to calculate that. That gives you 296. Okay, so now you know that your Z epsilon is LF minus L naught all over L naught. So you have 296.06 minus 300 divided by 300. Now, for some of you, because it's going to be a negative, you are scared. Oh no, cannot have negative. This is compression. Because it's compression, it's going to be negative. If it is elongation, it's going to be positive. So the answer must be negative because it's compression. It's going down. It's going down. So your answer will be minus what? Minus what? Okay. Whatever you say, I believe you. Who is that student? Oh, Fatin is very good. I trust Fatin. Oh, Shafiq, excellent. Who is that one again? Oh, Sarah Obaela. Sumo Baek. Okay. So, Adaswala. Like I said, the negative sign indicates that it's in contraction. So don't take off the negative, allow it to be there, just to show that it is in compression or contraction. Compression will produce. Any question? Let me look at the last one, then we close. Adaswala. Hello, kawan Adaswala.
Tadi sir.
Check up lah. Ayo.
Ada soalan.
Now, okay, so the last thing I'll be looking at is shear strain. Like I said earlier, shear strain is change in angle. Now listen to this. Change in angle sahaja, not change in angle divided by original angle. No. For normal strain, change in length divided by original length. For for shear strain, change in angle sahaja. So normal strain is defined as a measure of change in angle between two line segments. Ni original angle, ni final angle. Angle original, total angle final is equal to shear strain. So all you need to do is calculate your original angle, calculate your final angle. Your original angle, total final angle is equal to shear strain. Finish. So your shear strain is original angle minus your final angle. Ni final, ni original. Okay. And in most cases, if you have something like this, your original angle will be 90 degrees, which is pi all over 2. So if your original angle is in 90 degrees, which is pi all over 2. Okay, now wait, before I go into that. Okay, so for example, your original angle here is 90 degrees. Your final angle here is 84 degrees. What's going to be your answer? What's going to be your shear strain? What's going to be your shear strain? 6 what? 6 degree. So for your shear strain, there is a unit. For shear strain, there is a unit. But we don't use degree. You convert your degree to radians. So for shear strain, your unit is radian. You convert your degree to radians. For normal strain, add a unit. For shear strain, add a unit. So you convert your degree to radian. Faham ta faham? Okay, so here if we convert 90 degrees to radian, it's going to give you pi all over 2, then minus final angle, and this is in radian. That's all. So if you know your original angle, you know your final angle, you just tola, you get your shear strain. Very easy, eh? Okay. So since your original angle is 90 degrees, then you can rewrite this like this, which is your pi over 2, which is 90 degrees in radians, minus your final angle in radians. And with that one, if your final angle is smaller than your original angle, it's going to be positive. If your final angle is bigger than your original angle, your strain value is going to be negative. This is to tell you that your strain angle could either be positive or negative, if it is in compression or in tensile. All right, so we look at this example, and I think with that we close. So they want you to calculate your shear strain in this. So you calculate your original angle, you calculate your final angle. So this is final, this is original. So your shear strain is original minus final. So I want you to calculate your final original angle and your final angle here, and tell me what is your shear strain. Let's do that now. If you understand, let me know. If you understand, do. Doing that, I'll just be taking your attendance, so I can just make sure I'm taking time. Ayman Afik. Ayman Afik.
I'm here. Please here.
Alif Aika.
Yes, sir.
Alif Aika.
Yes, sir.
Where are you? Where? Cannot see. Amiru Wafi. Amiru Wafi.
Yes, sir.
Okay, thank you. Bastria, I think I see Bastria before now. Logan is here. Ifan Isiam. Ifan Isiam.
I'm here. I'm here.
Okay. Mazdika.
I'm here, sir.
Okay. Megat.
Yes, sir.
Megat. Mohammed Farhan Fidaus. Mohammed Farhan Fidaus.
Ada, sir.
Okay. No Ikmal bin Asmadi. No
I'm here,
Ikmal
sir.
bin Asmadi. Okay,
Yes, sir.
okay. Shafiq bin Bakri. I think I see Shafiq before. That's
Yes,
okay.
sir.
Yes, okay. I think I saw your name before. If you respond during my class, I will know you are there. Azik Baharuddin. Azik Baharuddin.
I'm here.
Okay.
Yeah.
Lagi is one. Mohammed is one.
Yes, sir.
Mohammed, this one